All right, Logan, you're up.
Hi, Dr. Hammett. How are you doing this morning?
Good. How are you?
I'm doing pretty good. I
Cool.
had a question for you about problem 10 of the homework set that's due this afternoon.
Okay.
I did watch the video where Katie was asking you about it, but I was still confused about a couple aspects of it.
All right. So which aspect of that?
Um, a couple things. First, you said that somehow we could apply the theory and the Burnside theorem with like extra restrictions, and I didn't quite understand how we could just kind of ignore the fact that um, adjacent bands must have different colors. Like that seems to complicate the problem significantly from one of the examples earlier in the chapter. I don't really know how that's working.
Well, so the way we set up Burnside's theorem with that original example with two coloring the squares, we just we didn't put any restrictions at all on the colors at each one of the vertices, correct? And we also just considered all the possible symmetries of that thing in three-dimensional space. We even allowed it to flip over in various ways, right? And rotate around. But we didn't have to, both of those were kind of artificial restrictions. We didn't have to do that. We could have said, look, I'm only going to consider colors that, I'm only going to consider colors that, or colorings that have, you know, um, well, that's kind of a dumb example. In this case, I can't say that all the colors are different in the case of vertices of the square, right? I'm gonna have um, I'm gonna have some vertices that are the exact same color, but that is a sort of restriction that I could impose on it. So, for instance, let's just do an example. What if I were to color, triangles, the vertices of the triangle, of the equilateral triangle, and let's do three colors. Okay. Then if I wasn't paying attention at all, okay, if I wasn't paying attention at all, oh, and by the way, let's only look at it under reflections or actually under rotations. Okay. So what are the rotations? Well, there's 0-degree rotation. There's 120-degree rotation. There's 240-degree rotation. And then we're back to the beginning. Does that make sense?
Mm-hmm.
All we're doing is we're just going like this. Okay. All right. So how many, like if I just colored the vertices wildly here, okay, or actually three colors under rotations, let's say with all different colors. Okay. So let's think about that. So how many options would I have for like the top vertex?
If that's the one you're starting with, you would have three.
Yeah. Okay, so there would be three options here. And then what?
Then there would be two,
Uh-huh.
and then that one would be determined.
Yeah, that one would be determined right there. Okay. So there's 3 times 2 times 1 colorings without respect to rotations. Okay, that's without respect to rotations. So I'm not paying attention to rotations at all, but I know full well that some of those, like if I rotate, I might end up with the exact same thing. You know what I'm saying?
Mm-hmm.
Okay, so and Burnside's theorem is going to take care of that for us. So this is our group. right? So this is our group right here. Our group has size 3. Okay, and N is equal to the number of equivalent colorings under G. Okay, this would be 1/3. Okay, and then I would have to add up all of the psi of these operations. Okay. So how many of the colorings are left fixed by 0-degree rotation?
3 factorial.
3 factorial. All of them. What about the number of things that are left fixed by what about the number of things that are left fixed by 120-degree rotation?
So we could pick one of the vertices colors, and then the others would have to be fixed.
Yeah, that's
So
right.
that'd be
because it's
3.
right, because it's a 3 cycles. That makes sense. So there are 3. And then what about 240-degree rotation?
That's the same because we can consider it 120 in the other direction.
Yeah. So this is 12 divided by 3. Which is 4. Okay.
Okay.
So interesting. Okay, so let's kind of think about why that would be true. So I don't know. Let's see here. Red, green. Okay, so it's like red, green, blue. Okay, so that would be one of them, I guess. Is there really 4? Hang on a second. One-third times that. Okay, well, what about this? Red, blue. Oh, what am I writing here? Green, blue. Would those be non-equivalent?
Yeah.
How in the world is there going to be 4 of these? I think there's 2, right? What in the world is going on? 6, 12. Okay. Hmm. That's weird.
Yeah, that's very weird.
Hmm. Well, let's look at, hang on, let's look at the specific example. Yeah, that's weird. I'm gonna have to think about that. Let's think about the specific example though that you were asked to deal with, right? So it was like this in-band baton or something, right?
Yes.
So here's like n equal to 3. And let's look at this. So like n equal to 4. Let's just look at these two cases, and I think we'll see what's going on in general here. And how many colors did we have?
We had 3.
Yeah. Okay, and the way that we kind of initially colored these things, let's first do this one since it's easier, is you had 3, and then you had 2 options after that, and then you had 2 options after that, right? Okay.
Mhm.
And the only thing that we were considering was, okay, yeah, but some of these I could rotate by 180 degrees
Right.
and get the same thing. So the group was just 0-degree rotation or 180-degree rotation. Yeah. So the answer ended up being, capital N, which is the number of equivalent things, equals 1/2. 1/2 times what?
I'm trying to remember the formula.
Well, it was 1/2 times psi of 0 plus.
Oh, that's right. Okay. Yeah. I just got thrown off because I was thinking the denominator of that fraction was supposed to be the number of colorings, but it's not. It's the number in the group. So
Yeah.
I was temporarily confused there.
Okay. Well, 1/2. Okay, so psi of 0 degrees. So what's that going to be?
That's going to be all of them, right? So that'd be 3 times 2 times 2, or 12.
Okay. And then 180-degree rotation.
So the one on the outside would have to match, right?
Yes.
So would it be 6?
Yes, because you would just go 3 for the leftmost one, followed by 2 for the middle, and then the last one would be determined, yeah? Because that thing's in a little 2 cycle with the outside element, right?
Right.
So 6. Okay, so this thing is apparently 9 because it's 18 divided by 2. Yeah?
Okay.
Let's just think about this for a minute. Can we actually list 9? So let's see. Red, green, red. I'm using red, green, and blue, by the way.
Okay.
Right? Red, green, red. What else could I have? Let's do
You have
red, 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 red. Okay. I'm doing all the ones that are like rotationally equivalent.
Although we can't have the same ones touching.
Oops. Yeah. Oops. So I should put red, what? Blue?
Yeah.
Red. Okay. What else could I have? Green, red, green, green, blue, green, right? I could also have blue, red, green, and blue. Oh, what am I talking about? I'm right now I'm doing all the ones that are equivalent under 180-degree rotation.
Okay.
Okay, blue, green, blue. Okay. So all of those ones are equivalent under 180-degree rotation, right? That's kind of where the 6 actually came from. Now, what about other things? You think of other things?
Things that aren't equivalent under 180-degree rotation, but
Yeah,
that
that
do
give you
follow
something new.
Okay.
Yeah.
we could have any distinct sequence like red, green, blue. We could have like blue, green, red.
Red, blue, green. Yeah. What did you say?
Could we do the reverse of those?
Yeah, but the thing is, those aren't really new. Know what I'm saying? Because again, Burnside's theorem is going to automatically account for those kind of not really being different under 180-degree rotation.
Okay.
Red, blue, green. Is there anything else? I'm still missing one. Maybe green, red, blue. Does that make sense?
Yeah.
And green, blue, red, I mean, that's already accounted for. Okay, blue, green, red, already accounted for. Blue, red, green, that's already accounted for, right? So there's the 9 things that are rotationally distinct. But let's look at this example right here, because this is a little bit more interesting.
Yeah.
Case. Okay, so what about the even case? How many?
So colorings without considering rotation, we have 3 for the first, and then we have 2 for everything else.
Okay. And so what's going to happen here? N is going to be 1/2. Okay, so 1/2, and then we have all of them, correct?
Right.
which is what?
24.
Yeah. And then 180-degree rotation. Well, that's a problem. Are any colorings going to be fixed under 180-degree rotation?
Can you explain that a little bit more? Because that was another thing that I was still a little confused about when you were talking with Katie.
Well, you can't, I mean, for instance, suppose I put red right here. Then what color is going to be next to it? Something other than red, right?
Right.
And if I rotate that by 180 degrees, I'm going to get something different.
Okay.
So it's going to be like, red, blue. But then if I rotate it by 180 degrees, I'm going to have blue, red right there in the middle. Does that make sense?
Yes.
How many colorings are going to be fixed if, like, the sequence of colorings end up being different at every position in the baton? How many colorings are going to be fixed by 180-degree rotation in this case?
None, because the middle will always be a problem.
Yeah. Yeah. And that's actually going to be a general feature of the baton situation if I have an even number of positions to fill. Does that make sense? The problem is going to be always the middle 2 guys. Since they have to be different colors, 180-degree rotation is going to cause me fits. I'm going to have nothing that's fixed under those, right?
Okay.
12 here. Now I'm like extra curious. I actually want to write I mean, like in these early cases, it's kind of fun to just write them down, I think. So let's think here. Red. All right. I don't know, red, green. Let's first do the ones that are fixed under rotation, okay? So
Okay.
green, And once I know I have red, green, Logan, guess how it has to finish if I want it to be fixed under 180-degree rotation. It's going to be red, green, green, red, right?
Yeah.
Okay, what about red, blue? Well, then it would be blue, red. Yeah.
But aren't those breaking the rule though?
Oh, yeah, which is why, yeah, that's right. Those are breaking the rule. Thank you. Okay, so what are we going to have here? Because nothing gets fixed under 180-degree rotation.
Right.
Okay, so let's see. Red. Let's look at the ones that start with red. Okay, I don't know. Red, blue. I don't know. Red. Blue. Let's do red. Let's do, I'm doing all the ones that start with red. Red, and then we'll have maybe green, red, green, red, green. Okay, let's do red, green. I'm doing red in positions 1 and 3. Red, green, red, blue, and then red, green, red. Or sorry, I'm done with the green here. Yeah. Red, blue, red, green, or something. Yes.
Mhm.
There, I just had red in positions 1 and 3. Okay. I could have red in positions 1 and 4. Okay. And then I could have green, blue, or I could have blue, green. Okay, so the first batch was red in positions 1 and 3. This batch was red in positions 1 and 4. Yeah.
Mm-hmm. Do we need to worry about possibility of rotation when we're counting these? So that like if we have the opposite ordering of something, it can give us something else that we already wrote down.
Yes, we do need to worry about that, but that's why I put red in positions 1 and 3. There's no way, right? So like if I put red in positions 1 and 3, there's no way that under 100 rotation, I'm going to have red in the last slot if I do that. Does that make sense?
Right.
So if I
That's a good
rotate
point.
these first 4, I'm going to have red in the last slot and red in the second slot, which there's no way that's going to be a repeat. Does that make sense?
Yeah, that makes sense.
Okay, so these ones right here are new. Okay, and let's kind of sort out what things I'm missing. Okay, so let's do green in the first slot and green in the third slot. Well, I already have a few where that kind of happened, but in the other order. Do you see? Like this guy right here. Like green in position 1 and 3, if I rotate that by 180 degrees, that's kind of the same thing as having green in position 2 and 4. Does that make sense? Like if I were to rotate this thing by 180 degrees. So what new colorings could I have here? Maybe like red and blue. Okay. Then green, green. Maybe blue and red. Okay. And let's see here. Green, green. Right? I don't want to put red, red, but what about blue, blue? Is that an allowed one? So, and by the way, Logan, the reason I chose 1 and 3 for a pair of colors like red, red, is because I couldn't have red and red right next to each other. That was not allowed. Does that make sense? So that's why I first started with red in 1 and then red in 3. Okay, and then what else could I have? So I had red, blue, blue, red, blue, blue. I think that's about it, isn't it? Okay. And let's see here. Can I have, oh wait, were you rebuking me right here because this guy, these guys right here are really the same? Aren't those guys really the same coloring?
It looks like it, but no, I didn't notice that.
Okay, well, thank you for rebuking me, Logan. Okay, that guy's not new. Does that make sense? Okay. All these other ones are definitely different. So green, green, blue. I have the blue, blue right there. Would it be? I mean, what about GR, GR? Do you see that that would be the same as something we already have?
Yeah, the same as the second one.
Yeah, RG, RG, the one I've already blocked off right there. Okay, so let's see. Am I missing anything? GRB, GB, GR, GB, GB. GR, GR is something I would already have. Okay. So I don't know, maybe we should go to blues in position. Okay, so like blue, blue. Oh, by the way, no, let's not do that yet. Let's do greens in the first and last position first. So if I go green, green like this, then what do I necessarily have to have here? Well, I could have red or I could have blue, but if I have red right there, there's only one choice for what could go third. What's the only thing that could go third here?
Blue?
Yeah. And it's going to be no different if I put blue, red. Does that make sense? Because of rotation by 180 degrees. Okay. So I think we're done with that. So let's do blue. Let's do blues in position 1 and 3. And then what about it? If I do blues in position 1 and 3, um, okay, so the only ones I have to look out for are the ones that have 2 B's in them so far. Okay. Where's that? 2 B's. That would be this one. Is there any other ones that have 2 B's? This one right here. Okay, so if I have a blue in position 1 and 3, I'd better not to put 2 reds because that would mimic the very first one we wrote down. Okay, but what if I put green and then red? Okay, BB. What about red and green? Okay. And I actually I don't think I'm going to be able to do anything else. Okay, because it's either going to be red, red or green, green. And I think I've already accounted for those. So I think the very last one is blues in the last 2 positions, or in the first and last positions. And then I would have to have red, green in the middle. And of course, by 180-degree rotation, it would be the same. Is that, what's that? Do I have 12 total now? 1, 2, 3, 4, 5, 6,
Yep,
7,
you do.
9, 10, 11, 12. Yep. Okay. So you can kind of see that all of that complication is being automatically cared for in this little formula right here. So, I mean, what's the general formula going to be, Logan?
For the problem,
Yeah.
we're going to have 1/2 times phi of 0 degrees plus phi of 180 degrees, or sorry, psi.
Yeah.
And then that's going to end up being, well, the total number, so psi of 0 degrees is going to be 3 times 2 to the n minus 1.
Yeah.
I have to think a little bit harder about the other case. So it's 0 if it's an even number.
Yeah. plus 0. I mean, it's just sort of silly in that case, right?
Yeah.
Okay.
Uh,
What about the odd case?
So we had said for the case when n equals 3, the edges have to be the same. But if we extend that out,
Right. So if you had like 5. Right.
right? So we pick the first half, the second half, the baton is determined.
Yeah, that's right. So you kind of go to right here. Yeah.
Yeah.
Just like in this case, you went to right here.
So it's 3, and I had to figure out where the halfway point is. So
Yeah.
okay, so it's odd numbered.
Well, but it's just going to be, it's basically going to be half of, okay, you basically put a 3 right here, okay?
Right.
Basically going to be half of everything, like if you just removed the first thing, it's going to be half of the rest. Does that make sense?
Yeah, that makes sense.
So it's going to be 1 less than n, half of that.
Mm-hmm.
That's basically what happened over here, right? You put a 3 right here, and then you took for the rest of it, you took just half of the rest. So what's the formula?
It would be plus 3 times n minus 1 over 2.
That's the power.
Right. And then
So it's 2 to something. What's this power?
oh, I see what you're saying. We'll have n, won't we have n minus 1 over 2 of those?
Yeah. That's right.
Okay.
That's exactly right.
That's pretty cool that we don't have to think about writing out all the
Yeah, it's automatically cared for. It's amazing. And I'm really perplexed by this last problem. Think about that. This one I made up on the fly and now have no clue. I'm definitely
Yep.
doing something wrong here. But yeah. Yeah. I'll have to think about that.
Yep. You'll have to let me know if you figure it out.
Oh wait, I did figure it out. Oh wait, no I didn't. Never mind. Uh oh, I know what I did wrong. These shouldn't be 3s. Logan, you totally told me the wrong thing. This is all your fault. So so think about it. These were non-equivalent colorings under, so what about phi of 120 degrees? The colorings, all the colorings had to be different. You said, well, I believed you.
Oh, you're right. You're right.
This shouldn't be a 3. What should it be?
So it's phi of 120.
Yeah, psi of 120. Yeah. The colorings were all had different colored vertices. Is 120 degrees going to fix any of those?
No.
No. Is 240 degrees going to fix any of those?
No.
No. So really, this is just 6 over 3, which is 2.
Whoops.
Yeah. So that's what's remarkable about this. Like you had me panicked there for a minute. I was like, man, I know this theory is solid. Am I gonna have to correct the book or something? No, so basically you can restrict the colorings you're looking at. Okay, so you can kind of say, I'm only going to consider colorings where everything's different or like adjacent things are different or something. But you can also restrict the group. because I didn't just have to look at rotations. I could have also thought about like reflections, you know, like through axis.
Right. Does the
Could have done
work we
that.
did here the same though as if we had allowed reflections? Like, do we
I
have the same
think
answer?
actually, if we did reflections, here's what's interesting, Logan. If we did reflections, I think it would be different. I don't think there would be any, I think there would be exactly one distinct thing. Okay, so like for instance, what if I said, so, you know, this is a new, I'll just do it down here really quick. Okay, what if the group, so what would be the, yeah, what would be, so I would have 0-degree rotation, 120-degree rotation, 240-degree rotation, and what would be the reflections?
We could have a reflection as the line is drawn now
Yep,
through the triangle.
you could have that one. You could have this one, right?
Mm-hmm.
That's this, okay? And you could also have what?
You have that third
Yeah,
one where you're going from a point to an edge.
yep. Okay, so what would the answer for n be in this case if I instead bulked it up to this? So watch. N would be 1/6 because that's the size of the group, yeah? What will psi, okay, so psi of 0 degrees plus psi of 120 degrees plus psi of 240 degrees plus psi of this plus psi of that plus psi of that, okay? So let's compute this real quick. This would be a sixth. What's psi of 0 degrees?
Aren't those three the same that we just calculated?
Yeah. So it'd be 6 plus 0 plus 0. Right? I have 6 total, you know, harebrained colorings where I just colored them without paying attention. Yeah. 3 times 2 times 1. What about psi of vertical rotation? How many things are fixed by vertical rotation?
So if we have the three have to be different.
Yeah.
Is it possible?
No, because these would have to be the same color. Yeah.
Right.
The bottom 2 vertices would have to be the same color, and that's not even something we would consider. So look, and by the way, the same thing's going to happen with the other 2 reflections. So it's 0 plus 0 plus 0. And you're like, what? So what do we end up getting for the answer here?
1.
So there's one non-equivalent coloring if we include the reflections. And indeed, that's true. Look over here. Under reflections, what's going to be true about these guys?
Under reflections, they're going to be the same through the vertical.
Yeah, they're exactly the same. So this is the exact, right? When I include those extra group elements, suddenly I have, you know, I have another way of moving something and it decreases the number of non-equivalent colorings. Does that make sense?
Yeah, that surprises me though, because isn't that problematic? As I had thought you had said in lecture that we can choose a subset of the group and it would still arrive at the same answer. But these are different
No,
answers.
it would still give you the number of equivalent colorings. So if you choose a subset of the group, it will still give you the, yes, it will give you the right answer, but the answer would be different under that particular group setting. So in this case right here, where I only consider rotations, I get 2 non-equivalent colorings, right? And that's the right answer. But, right, we can actually look at it and write it down and we're like, yeah, that's the right answer. But then if I include reflections, suddenly these things which were 2 are now just one thing. Does that make sense? So it's not going to be the same answer because it's not going to be the same answer as you had like in the other group of, symmetries. It's just going to be the right answer for that particular one. So like if I take a subset of the group, it's going to give me the right number of equivalent colorings under that new collection of group elements. Does that make sense?
Yeah, that makes sense, because we have different operations that can permute. Is that a word?
Yeah, right. Yeah.
The colorings.
Different things that can move colorings around into one another. That's exactly right. Yeah. So look at that. Isn't that amazing?
Yep.
That example's pretty cool. Yeah.
Okay. Well, thank you. That definitely helps a lot.
All right. Well, I'm glad you asked, and I'm glad we kind of made up our own example. And
I'm glad I stumped the professor.
all right. Cool. Anything else, or is that it for now?
That is it.
All right. Well, hey, good seeing you. Good luck on your capstone presentation.
Yeah, thank you.
When is that?
That's tomorrow at 5. So
Okay.
I'll definitely be glad to have that over with.
Nice. All right.
Well,
Well,
thank you for your help today.
Yep. All right. See you later, Logan.
Bye, Dr. Hammett.